Good morning. Today is January 20th, 2018, and this is the John Chappell Natural Philosophy Society Science Chat. So today we pretty much have an open forum today, and I believe that Hans, he sent me a document. I guess he was inspired by his visit to the Virgo laboratory, and that's the gravity wave laboratory. And so why don't you tell us about your experiences there, Hans?
Well, I was there with a group of students and alumni of my university, and we got the opportunity to go there because they were in repair.
Excuse me, Hans. What are you talking about? Where is this place? What is it?
It's near Florence in Italy, and it's one of the three places where they can measure the pass-by of gravitation waves. They about a month ago or so, they measured the pass-by of the gravitation waves that were the consequence of the collision of two neutron stars, and they concluded from that collision that by such collisions, the heavier atoms are generated, and that was possible because they saw this collision coming, because they saw also the kind of vibrations that were caused by these very speedy rotations around a common center, and so they saw a final merge coming on, and then they warned 70 other stations with telescopes, normal telescopes, and those investigated not the gravitation waves but all the electromagnetic phenomena that go along with it, so light phenomena and electromagnetic waves that are coming from that collision. And from that they could conclude what kind of processes were going together with this very strong collision. This machine is a very, very fine measuring machine. They can detect difference in length of the 3 kilometer pipes of less than a part of the diameter of a nucleus of an atom. So they can do very sensitive measurements. Similar stations are in America at two places, one on the north, in the west side, and one on the east side, and they are called LIGO. So together they could find the location of where this collision took place. And we were astonished by the precision that these scientists there at that location were able to find such a very small signal, which was nearly buried in the noise. So they had to do a lot of extra measures to get this signal captured. And in fact, the Vigro itself didn't see so much because the angle in which it was detected was not optimal. It was much better for the LIGO sites. They had a much stronger signal, but Vigro had enough signal to see what was going on. Here on the picture now, you saw the graphs, the vibrations that they saw come by, and the whole thing occurred in a fraction of a second. So the final explosion, which occurred millions and millions of, I think, 10 or 20 light years away, occurred in a fraction of a second, and the sail has kept its shape when it was traveling in our direction. So we could see it as a kind of front, not a weather front, but a vibration front coming by. So from scientific reasons, it was a very nice occurrence because we could capture a lot of scientific data from an event that we else couldn't have detected, because normally we only see the aftermath, but never the occurrence. And here we could see things coming on because we got already signals in advance and saw it coming by. So we could warn other stations to also look at the same position. Does anybody, well, what astonished me on this is that these people measured very fine, but in fact, they had no idea what kind of waves were coming by. So I put a question, do you have any idea of the kind of waves that were passing? Is it a shock front, or what kind of waves are they? And they say, well, no, there are some theoreticians here that make trouble about that, but that's not what interests us. We are interested in the passage of these vibrations. That's the only thing we measure.
Well, whatever they're measuring, it's causing a shortening in the legs of the experiment.
Yeah. And at least one of the legs must be longer than the other. But the angle in which the micro was measuring was not in optimal position. It was nearly in the diagonal of the two legs. So it was not fully at 45 degrees. Then these things are perpendicular, but it was not far off. And the LIGO measuring sites were in a much better angle, so they get a much higher signal.
And now I myself, I did get an opportunity to visit the LIGO laboratory during the Great American Eclipse. The LIGO laboratory is not that far away from where the eclipse was happening. So a couple-hour drive, and they're having a special eclipse party. So I also got a guided tour of the LIGO facility.
Yeah.
Now mostly you can just go to their main control center, which looks like where they launched nuclear missiles. You've got a room that's just like filled with screens, and they've got like charts and graphs going on the whole time. Now, at the time that was there, they were saying that they had found something very interesting that they weren't going to say. So that may have been this announcement that you had mentioned, that they had detected a gravitational wave, and they had located approximately where it should have been. And then when they actually looked there, they actually saw some electromagnetic, like some visible light activity going on. And that confirmed that it was a genuine astronomical event that caused what they had detected in that area.
Yeah, because they were in repair, I could go in the buildings where these mirrors are situated. So we could go everywhere. And these mirrors are encapsulated in big cylinders, 4 or 5 meters high and 2 meters wide. So we couldn't see the mirrors themselves, but we have seen a lot of spare equipment lying around there, and they were replacing the way they attach the mirrors on two sides, because they must isolate vibrations from the environment very strongly, and they are now uh, exchanging the current way of hanging them up by a new way with new materials. But we could see a lot of these things. Their speciality is measuring the passing by of these waves, not what kind of waves these are. That doesn't interest them very much.
Well, I think it's interesting in that, you know, this is based on Einstein's gravitational waves, and Einstein always said that gravity bends space-time, whatever the heck that is. Now, I was never really quite sure what on earth space-time is.
Now, that's a mistake. These waves are already solutions of the wave equation. You don't need Einstein with this very complicated theory to understand these. These waves can be understood already with the normal wave equation.
Well, how is that? I've never really heard that explained. I mean, there's been a lot of people who research black holes. So I just recently saw, for example, on the Science Channel, there was a show called How the Universe Works, and they had a special on black holes. And, you know, they're questioning, you know, whether black holes exist or not, you know, or do they exist the way that people think they exist? You know, they always show like a background of stars, and there's a black hole, and it's just a black disk, and it has a event horizon, etc. But you know, these people spend their days trying to figure out, well, if this thing existed, and if two black holes collided, then exactly what would that look like?
Yeah.
So they do all their calculations, and basically this is what LIGO and Virgo are looking for. I mean, they get an awful lot of signal coming out of their experiment.
That they have detected about 3 or 4 times black holes, but the last time they detected 2 neutron stars. They are not black holes, so these are normal massive bodies, and they make the similar kind of waves when they merge. So the same kind of waves that do the normal bodies can also describe the merge of black holes. Uh, at least what you can see of them at a very far distance. And these were all at far distances. And I think several tens of millions of light years away. And then the solutions are far more simple than when you are very close to the occurrence. And these, what is passing by, those waves can easily be described by the wave equation.
Well, it is a wave. I mean, it's not a very complicated thing to describe, which is just like, you know, two things swirling around each other until they finally hit. I mean, I think probably anyone can intuitively see how that could work.
Yeah, there are also some vortexes involved.
That they're not bending.
Sorry.
It's like, I don't know, if you did this experiment in your bathtub, you know, probably you could see similar kind of waves, right?
Yeah. It's a very, it's not a very complicated thing what's happening there. It's not too difficult to describe.
As far as, you know, you're asking, you know, exactly what a gravity wave is, and like I said, I don't think it's as complicated as space-time. Whatever these waves did, they actually compressed the experiment in one direction versus another. And the way I would think of it is that if you had like a 1,000-ton cube of lead or something, and you stood right next to it, you would find that you would be gravitationally attracted to that gigantic cube of lead. And because of that, some of your atoms are compressed in that direction. So you'd actually get, a little bit, compressed just because of the action of the gravity compressing the atoms together. So that's how I see what this gravity wave is, and that if I mounted this block of lead on a rail and I moved it back and forth, then if I had a very sensitive force meter on me, then I could see the force increasing and decreasing, and that would be a more simple way to see what a gravity wave is, right? It's just an increasing and decrease of gravitational strength.
Mathematically, you can treat the electromagnetic field and the gravitation field with the same equations. There is no, with respect to the equations, there is no difference in these fields. The way that these fields are triggered, there is the difference. So the start and boundary conditions of these two fields are different, and that's why they appear to us in a different way. But the mathematics behind them is completely the same. That's why the vibrations also run with the same speed. The gravitation waves and light waves and all those things that run in a free field are running with the same speed. It's the same mathematics behind all those fields.
Well, I've always made a distinction between gravitational interaction, I mean the force of gravity, and gravitational waves. I think what you've just said about gravitational waves is true, and indeed what Franklin said. They appear to be governed by the standard wave equation, and they seem to be due to some sort of compression and rarefaction caused primarily by gravitational means, and therefore are analogous to electromagnetic waves. However, and therefore probably do travel at the same speed, the speed of light. But the gravitational interaction has been shown to be fundamentally different. I mean, that travels practically instantaneously, maybe thousands of millions of times the speed of light. So I think you need to make a distinction between gravitational waves, which we're a bit uncertain concerning the nature of, and gravitational interaction. One other thing, just while I have the floor, there have been a number of papers, in the dissident press, but elsewhere as well, maybe casting some doubt as to the veracity of the interpretations given by the LIGO and the Virgo people and so on. I'm just asking Hans, have you any skepticism about the official position that they've taken? I mean, you seem to be, repeating it. I'm just wondering, have you any skepticism about their distinction concerning, random variations and noise, and have they really filtered all this out?
I think they took every measure that you can think of to avoid noise or to reduce noise in the measuring results. And what they measured was just above the allowable signal-to-noise ratio. It was just above the noise. The signal was so weak that other instruments that were built in the past never could capture it. They had, with all these, I think they took about 10 or more different measures to reduce noise and to improve the signal. And that's, in fact, the only thing what interests them is to capture the gravitation waves, the difference in geometry that was passing the measurement location. That was what they were after, and not the waves themselves. They didn't care about the kind of waves that were passing by.
So in other words, they weren't claiming that these waves proved Einstein was correct.
No, that was not
They
what
did.
they were testing. They just tested that something uh, made a difference in two directions. They have two pipes, 3 kilometers long, in which the light was traveling up and down about 10 times. Um, into these two legs, and what they measured was that there was a difference in length between the two pipes. And that's all what was measured, nothing else.
Okay, I'd like to interject here a little bit, if you don't mind. There was a program on Nova that came out last Wednesday here in Virginia. Is there anybody out there that saw that Nova program that talked about this? Am I the only one who saw that?
I have not
Well, I
seen the
tried to
program.
watch that. That can't be watched online, except it kept on stopping on me. Yeah, there was like a 2-hour Nova special on black holes. So what were they saying exactly?
Well, basically, I didn't watch the whole thing. They were reporting on the LIGO experiment and claiming that the LIGO had proved Einstein's theory correct because not only had they detected gravitational waves, but they had detected black holes and et cetera, et cetera, et cetera. So the whole thing was like, wow, Einstein was such a great guy and he's so correct because he predicted all this stuff. And I was somewhat skeptical of that claim. So I'm just asking if anybody saw that program or not. And I'm assuming from what you're saying, Franklin, that you tried to watch it online.
Yeah, it's available on pbs.com.
Okay.
So if you missed it and you wanted to watch it, you can try and have it streamed.
Couple of points, if I might make a couple of points here. Detection of gravitational waves has been claimed for 20, 30, 40 years. Weber claimed that he reported detections of gravitational waves. And so this whole business goes back, it's not something that just started recently. They've been detecting these waves or whatever they're detecting, and various detectors have been constructed for years and years. And over that period of time, they've been improving the technology and the the equipment and the techniques and everything that's involved in it. And so, it kind of comes to me as a surprise. They say, oh, now we've detected and proved that gravitational waves actually exist. And, that's really just not new. What's new is that they've sort of reduced the uncertainties, if you understand what I'm saying.
What is new is that they did it with three different measuring sites that were distributed over the world and far apart.
Right.
And they detected it.
So they So they removed the arguments that this is not a repeatable measurement. When Weber did it, he originally had these gravitational wave detectors. One was in Maryland and another one was like somewhere near New York or New Jersey. And he reported coincidences. In other words, they detected coincidences. The wave would be detected at both places. Now, I'm not really familiar with all the work that he did, but this was reported 30, 40 years ago. So this is not particularly new.
I understood from the people from Figaro, and they said the Weber measurements were proven as false. I don't know why, and I'm not an expert on that, but that was what the Figaro people claimed.
Well, that's my understanding, but obviously they must have thought there was something there, or else they would have abandoned this line of research.
I think most people that understand something of gravitation have always known that there must be gravitation waves, because our living space is a field and it can vibrate. And that's what everybody in fact knows, because otherwise gravitation force wouldn't exist. That's the static form of that same phenomena. And now we are seeing the dynamic form of it. But we already knew that there was something there, and it moves, for example, with the planets and the stars. So it is a dynamic phenomena. For us, it is static because we only see it here on Earth and always working in the same direction. But the moon is capable to make a definite signal that we can see if we go to the beach.
Okay, now here's another issue that I want to mention. Did they explain why they say they were neutron stars and not black holes?
They could see afterwards what was going on when they also draw the other star, how you call it, all other measuring stations. They had informed 70 different star watchers to look at the same location. They found at what location something was happening, and they could guide them to the same place. And all these saw the same explosion. And from that, they could conclude it was a neutron explosion. All the collisions of black holes didn't give any after signal, because it was black what was resulting, and this time there was a star resulting.
Well, that seems kind of vague to me, but anyway. All right.
That was what they said. I'm not an expert in these things, so I cannot comment very well and assure you. But I think also what was in the press, you hear about the same stories each time. It was interesting. We also saw a laboratory of the university in Florence, because there they have the people that build these high precision optical instruments, and they do a lot of different optical measurements and all kind of very fine sensed experiments, and a lot with light. And so at a given moment, I asked them, can you tell me what the structure of a photon is? And the answer was, that doesn't interest us. We know how photons behave, how they behave as a particle, and how they behave as a wave, and that's all. We don't need to know what the structure of a photon is in order to do our measurements. And that astonished me to a certain extent. These people do very fine measurements with things of which they themselves don't understand, not the internal structure.
Well, that's no surprise. I mean, that's, I mean, kind of, that's not really new.
Yeah, but
the
good.
Experimentalists and the theoreticians really basically don't,
They don't even understand how gravity works, right? For heaven's sakes, nobody knows how that works, right? But yet we can do these experiments. Right?
I think I know how it works. but then you have to read my papers. But no, and I also know how a fountain is structured, but uh, at least it is not common physics. Physics doesn't bother about it.
Does anyone know if gravity waves are considered to be transverse or longitudinal?
They're transverse.
Gravity waves?
That's the claim, yes. I've got a book here
Well, I'm
that'll
not sure
show
how you
you
could
a
really
picture of a
tell.
gravity wave if you want.
I think these phenomena that were seen are not waves because they have, in fact, no frequency. They are fronts. It's a kind of shock front. I couldn't get assurance about this, but it is passing by in a fraction of a second, and then it's gone, and there's nothing behind it.
Yeah, it's more like a
I
boom.
don't know if it came up, but the question of aberration on these waves, did that come up? Because if there was a similar aberration to that of light or electromagnetic radiation, whatever they use to detect these so-called neutron stars, well then, you would have had a wave which was traveling at the same speed and was subject to the same aberration owing to the Earth's motion.
I think people have still to make a distinction between waves, which have a frequency, and fronts, which have no frequency, but also can pass through fields and work with light speed. Fronts can, for example, one-dimensional fronts exist and keep their shape and their amplitude. Spherical fronts keep their shape but diminish their amplitude as 1 over the distance from the starting point. So that's why the final signal of this explosion was such a tiny signal. The amplitude has gone down to a very small degree, such that we could hardly measure anything here on Earth. But light is a one-dimensional phenomena. It's a string of shock waves, and these keep their amplitude. These can travel billions of light years without losing their amplitude. And that's why we, after such a trip, we can still detect them.
Just another question. When they subsequently analyzed the position in space where these disturbances appeared to be coming, excuse me, was this done by optical means or by, say, radio astronomy?
So the position was predicted by the results of the first detections of things passing by. So they had signals measured at 3 positions, and from the strength of these amplitudes, they could see in what direction they had to look at the universe. Especially the fact that the Vicro signal was very small compared to the LIGO signal, and it must be the same signal. They could know that the diagonal of the 2 pipes must point nearly in the direction of where the things were happening. They could locate certain areas of the sky where this event was happening.
But it's a bit of a circular argument because they're using signals to verify the reception of signals. I mean, they haven't actually verified the position of these neutron stars by, say, optical means or other means, have they?
They did it by using the signals measured by Vigo, the 3 the LIGO and the Virgo stations, the 2 LIGO stations and the Virgo station. From From that fact, they could derive the location of where this explosion was taking place.
Okay, I suppose what I'm saying is that you have a number of independent observations of the same ostensible phenomenon. I do accept that, but you haven't actually verified it by some means outside its own measurement system. So it wasn't a repeatable experiment in the sense that you could actually go and verify it, do it again. But you simultaneously, if you like, had three independent observations of the same spot phenomenon.
There was some trail, there was some warning trail before the explosion took place. There was these things were encirculating faster and faster around each other, and that was already visible in these measuring instruments. And that's why they had sufficient time to warn the other stations, the other 70 stations, to look at that location. So the final
Do you
merge.
guys see the graph I'm putting on here? The graph of Hanford, Livingston, and Virgo? Are you guys seeing that chart?
Yeah.
I mean, this is the actual data here. So
yeah, that are the measuring data, and these first signals. That is a very short time. That was enough to guide the other stations to the proper direction.
Now I'm looking at this data. Now they've got the big dark line here through the middle here, which is not the actual data, I don't think.
That are the
but is probably an average of the data.
That are the actual data from Vigro and LIGO 1 and LIGO 2.
Yeah, but I think the actual data is what's in the light line. Like there's a red line under Hanford, light blue line under Livingston. I mean, this is the stuff that's going on in here. And then there's this purple line that represents Virgo. Now, if you look at the data that Virgo provided, I mean, you can see that the magnitude in Virgo, especially when it started, is as large as the rest of the signal. In fact, if you erase this big dark signal, which they're thinking is the average, I would think you'd have a very hard time actually seeing that there's a signal in there.
Yeah,
so I'm kind of wondering how they're processing that. I mean, I can kind of see the signal in the Hanford plot, and the Livingston one is pretty clear, but the Virgo looks almost like noise, and that they plot this nice, neat, dark line through that entire mess. I'm not exactly sure if that's legitimate.
I don't know. They concluded positive.
Because this is basically what they calculate, right? It's like, okay.
Yeah.
And if we went and we go and we overlay that over random noise, it's like, yeah, it's going to match. Yeah, it's like, if you're going to just completely ignore this part of the graph on the left-hand side, just completely ignore that, and then just kind of look at the middle bump there, and then completely ignore everything that happens after that, then sure, it's a match, but it's like not by much. But I don't know. You asked about what doubt we might have about these kinds of measurements, but it's like if that's the raw data and this is what they're matching it to, it's like that's not, it takes a certain amount of imagination to agree that that's what's going on there.
It's the top of capabilities of science at this moment.
I had my doubts about LIGO just because of these data processing things. Since basically these experiments can only detect these kind of black hole mergers. I mean, if there's no other actual kind of gravity wave they can detect. I mean, if you ask them what other kind of gravity incident you can detect, I don't know, like a supernova or something like that.
No,
I think they probably say they can't because they don't know what to look for in that case. So it's kind of a case that that you've got some source of signal, and let's basically just call it like complete noise, and you've got a certain signal that you're looking for. Now, eventually, the laws of physics say that everything can happen as long as it's not specifically forbidden, that eventually your noisy signal is going to produce the event that you're looking for. So if I'm looking at, say, a screen that's not tuned to anything and it's just white noise, and I predict I'm going to see a Mickey Mouse ears pop out of there, that, you know, eventually, and if that happens, then I have solved, you know, the solution of, you know, what gravity is. Now, eventually, if I see the Mickey Mouse ears, they'll eventually happen. But does that really mean anything? That is kind of the objection that people had
Yeah, but
to
here,
this kind of analysis.
here they measured an event that has some history. Eh? There's a trail in advance. There is the merge, and then also some after signal that there was something is still rotating there. That's the final part of the signal. If there is only one event, then it's very difficult to detect this at the same time. And it's since shortly that these three stations are working together. Up to so far, a few months ago, there were only two of these stations measuring, only the LIGO systems. Now there are three of them, and in the next future, there will be far more of these stations that measure together the gravitation waves. If they measure in synchrony, you have the chance to get far more data and correlate them.
Well, Hans, my
Yeah,
particular question goes to the fact that you said that they don't really know what kind of a wave it is, or you know, that's what kind of piques my interest, in that they are not interested in what the wave is, or
they can only think about what kind of they are not measuring the shape of the waves.
So that goes to what Ian was asking, which is whether the waves are transverse, or so they can't really prove that they're Einstein gravity waves because they don't really have enough measurements.
No,
the machine doesn't really do that.
They only saw something coming by, some vibration passing by, and it was a kind of a front that was passing by.
Ian,
by the way, this isn't really raw data here. This is highly filtered data. The raw data is like 1,000 times stronger than this stuff.
Would you like for me to explain what they did?
Sure.
They use what's called a match filter, which in electrical engineering is a kind of a development of information theory in electrical engineering. Basically, have you ever heard of coding theory? Do you know what coding theory is?
Not really.
Well, the reason that digital communications is very effective is because they use what's known as coding theory. And what you do in coding theory is you basically take a set of data and you encode it in a certain way. And when you encode it in a certain way, you know what the code is that's been put onto the data. And what they do is, since they know the code that was transmitted, when the code is received at the receiver, they can figure out what was corrupted by noise. So in other words, they can take the noise corruption out of the signal because they know what the signal was that was transmitted. Do you understand that concept?
Yeah.
Okay, this is basically doing a similar type of thing. They're looking for a signal that is transmitted, okay, and they can strip the noise off of it because they're looking for a signal that they know was transmitted that is being received. So they're looking for something that they know was transmitted when it's received. And the match filter basically does a calculation of the best estimate of that signal that was transmitted. So what you have to do in order for this to work is you have to know what was transmitted. And they do that by through the orbital calculations of these pulsar stars or black holes. They have a theory that tells them what kind of gravitational wave would be transmitted by a merger of black holes or neutron stars. And then they compare all the noise that they receive to the signal that they're expecting to be received. And then they do a statistical estimate. Does that make sense to you, what I just said? It's kind of a very brief explanation.
Yeah, the problem is that they don't know how fast these oscillations are increasing with their frequency.
Well, it's not really clear to me exactly how their algorithm works, but what I think they do is they search through thousands and thousands and thousands of possibilities using a high-speed computer.
That could
Yeah, I
be.
read that they actually inject fake signals into the data to see if the analyzers can detect that it's a fake or not.
Well, yeah, but the real trick here that you have to understand, here's the key point. You have to understand this idea of a match filter. You can't do the match filtering unless you know what the signal was that was being sent. And so what they're doing is they're looking through their database of possible signals that could be received and going through and iterating all these parameters and matching it to this match filter algorithm, and then finding a kind of best matched fit. Do you understand what I'm saying? The best match fit.
And
Well, I'm thinking that's what we're seeing in the graph here.
They're trying to correlate between do correlations between the three sites, right?
Well, no. Let's just not ignore the three sites, just at one site. Okay, so they're looking, they have in their database of their computer all these simulations of black hole mergers, if you will. Okay, and so they have all these signals in a database. I'm sort of essentially trying to simplify it as much as I can. But in essence, what a match filter does is it knows the signal that's going to be received, and it tries to extract that known signal out of the noise. And it has a filtering algorithm that does that. So you have to start off with that you assume that you know what the known signal was to begin with. Okay?
Yeah, I mean, that makes sort of sense, but then...
So all of they've done here is they've looked through all these signals that they're constantly receiving. They have this computer that does all these computations and all these on the signal, and it compares them to all these different possible signals that could be sent. In other words, it tries to match the signal that's received with a prediction of what the signal ought to be based on a theoretical calculation of what a black hole merger or a neutron star merger looks like.
Yeah, but they have not so much measuring data of these mergers. They've measured only a few of them in the past few months. So
right, but they predict theoretically what the waves would look like that would be transmitted by one of these events.
So there's a technical description of the circularity that I talked about earlier, that it really was a circular argument. I mean, you're not starting with a blank slate and then getting some information. You're starting with some types of signals that your theory or some of your observations have indicated in the past might exist. Then you're popping them into this filtering match system, and then you're saying, well, if that signal is really what originated, well, then I've eliminated all the noise, and therefore it is correct. It's verified my signal. It's a bit of a circular argument.
Yes, it is. As I explained, in electrical engineering, the way digital communications works, and the reason that it works is because you know the code that was applied to the signal that you encoded, and then you know, based on what the noise is, what the signal ought to have been that was received when it's in error, because you know the structure of the code. So you have to know the structure of the code in order to correct for the errors.
You're talking about like a CRC kind of thing?
Yes, that's an example of a kind of a code, yes.
But I mean, I think you can see that I've enlarged the plot here of the data here. So looking at the LIGO data, you know, I think so. Harry, you're saying that this dark line that they have here, that is basically the signal that they had predicted that they were looking for, and so they're basically extracting, because this black line isn't the actual signal. The actual signal is this little red squiggly line that's going all over the place that obviously has a whole bunch of noise in it. But out of all that, they're extracting out their black hole signal, even though it doesn't exactly look like
that signal. Let me go over this again. Maybe it'll help you a little bit. In the old days of radio, you would have what's called a CW signal, a constant carrier signal on a constant single frequency. And what you would do to receive that signal is you would create a filter that only would receive the frequency of that signal. Does that make sense to you? You obviously don't understand that concept.
Well, isn't that like how AM radio works?
That's how radio works in the old days of radio when we do Morse code, da 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 da. And in theory, what you can do is you can make the bandwidth of the receiver so small that it eliminates all the noise and only captures the energy of the signal you're trying to receive. Does that make sense to you?
Yeah, I mean, I think I understand these concepts.
So what they're doing here is a similar type of thing, which is that you match the filter that you're using at your receiver to the signal that is being transmitted. And when you do that, you maximize the energy of the signal that's being received, and you eliminate the noise energy. And so what you do is that increases what's called the signal to noise ratio. And a match filter is a device that optimizes the amount of signal energy that's received and rejects the amount of noise. So you basically are you're trying to optimize the signal that you're receiving and rejecting as much of the noise as possible. And then what they're doing is, by the fact that they can predict in advance what they think the signal ought to be, they have match filters that look for signals that they're predicting in advance based on their theory of what these signals ought to look like.
So that may be a legitimate thing for them to do.
It's not a question of a legitimate thing for them to do. That's what they're doing.
Yeah.
If you think
but for me, when they actually found the neutron source, and when they actually found the neutron visible north, that was okay.
That's basically your opinion, I think.
What I've seen there on measures were mostly optical measures to get their optical signal as noise-free as possible, with no noise from the environment. And then what they measured was the clean signal, the difference in length between the two pipes. That was the signal, and I haven't seen that they had an extra signal processing on top of that.
Well,
They didn't mention that.
well, that's probably because they didn't want to reveal the. It's very difficult to understand what I just explained, but from what I've read about the literature, now here's the thing: what you just said. If I am trying to detect this match filtered signal, the system can only work down to a certain signal to noise ratio. So they're operating at negative signal to noise ratio. When I apply this match filter technique, if I have more noise to start with, then it's more difficult for the match filter to operate correctly. So obviously what I do, and this is what we do in electrical engineering all the time, is we try to get rid of all the noise sources that can affect the results in our system. So we make sure that our antennas don't generate any noise, and every stage of our receiver we eliminate and try to get rid of as much noise as possible. So we reduce as much as possible the incoming noise, and that makes it more possible to detect weaker and weaker signals.
Yeah, the problem is that these are one-shot signals. They have a trigger, and then they run off, and they don't repeat. So you cannot do all those tricks that you can do with signals that have some synchronizing possibility in them.
Well, apparently they must have been able to detect something because they had an advance notice. So what they're saying in effect is when these neutron stars are rotating in orbit around each other, gravitational waves are being emitted as they're orbiting around each other. And
yeah, but that's not a stable orbiting. Eh? The orbiting
right.
is the frequency of that orbiting is increasing very fast, and not in a way that you can foresee.
Franklin, go back and put the signal waveform back on again.
Okay.
Yeah, it seems kind of suspicious that these astronomical events occur in a tenth of a second. When you've got light years.
No, well, the merger occurs very quickly, which is that peak at the end.
Even
so
that,
in other words, what they say that it's like a ringing of a bell.
How can that take place in a tenth of a second? It seems weird to me.
Well, I don't know. I can't really explain that. The issue is that this merger that takes place, which is the peak, the signal sort of starts off with some oscillations and then peaks at a peak and then stops. It's that peak merger which is at the end. Now, presumably prior to this merger, the stars are orbiting around each other, and in the process of doing that, as they're approaching the final merger, the final denouement of exploding and merging, there's gravitational waves being emitted. That's what the theory said. And so this device starts looking for these oscillations of these gravity waves and at a certain period or a certain frequency, and using this match filter, it looks through all these possibilities until it finds one that looks like, it's meets the statistical criteria for a positive detection.
But these graphs that you saw, they cover only a few seconds, huh?
Not even a few seconds, like half a second.
The gravitational waves supposedly that are being emitted have their maximum just prior to the merger. So the maximum amount of gravitational energy is emitted just as the two stars sort of swing around each other and get sucked into each other. That's when the maximum amount of energy is radiated.
All these things, these up and down moves in the graph are gravitational vibrations.
Correct. According, that's the presumption that they think they're measuring. That's what they think they're measuring.
That's what they measure.
Well, the theory says that's what they're measuring, yes.
Well, this came out of the instrument.
Now, who was asking about whether they thought gravitational waves were transverse? And why would you ask that question? Is that have any relevancy?
A front is always transverse.
Well, here's the picture. I'm going to put the picture up
asking
on my
about whether gravity waves are transverse or longitudinal, or
supposedly looks like. I don't know if this is going to help any of you.
I think maybe just a comment. One thing is coming out of this that
you notice that it looks like it kind of pushing out at the top of the slide.
let's see. You're trying to show us something, Harry, but you're breaking up.
Yeah, I could hardly hear anything there.
Yes, Ian.
Well, I was just going to say I could hardly hear you, Harry, but just a comment that it appears that even though you visited this with a scientific group, and they've obviously done all these experiments and work and so on, the sort of PR, if you like, that they would give would not go into details such as we are now analysing. Transverse waves, aberration, signal processing. They wouldn't mention anything like that. I visited the LHC in 2008, also with a scientific group. But again, it was fairly superficial what they gave us. And I can understand that because they put it into the PR department where they're given certain headlines and they don't expect people to start analysing it. And if they start putting in these factors, well, then people will start questioning and they'll get confused, and the media will say that it wasn't a crisp experiment. So I think with respect, Hans, even though you were with a scientific group, you were sort of given a bit of a, I don't know if I'd call it a PR spin, I'd call it a simple, I was going to say simplistic, a simple explanation of what was actually happening. And we're now in a little difficulty because, being of our nature scientific people and distant maybe, we're now questioning the very basics of the things, and there mightn't always be answers. I just want to...
They didn't do any.
Yeah, may I ask you this?
Any signal processing.
They didn't do any signal processing.
Well, they didn't talk about any.
They didn't talk. That's the point I'm making. They didn't mention that at all.
Yeah.
Thank you.
What they showed is all measures that they took in order to isolate environmental noise, so vibrations from the environment. So what they measured was exactly the difference in length of the two pipes and the dynamic change of that length difference. That's what the graphs are showing.
All right. So, what about the more fundamental questions, like what is the wave that's actually going through? I mean, is it truly related to gravity? I think the point was brought up that if we saw the neutron stars doing something, could that have possibly been some kind of electromagnetic interaction rather than being gravity that's causing the LIGO experiment to contract in one direction? I mean, one area of interest that I wanted to get in today, which is just the nature of the electromagnetic wave. We've actually had quite a few emails going back and forth, and the way that the electromagnetic field is commonly shown is with this, someone mentioned transverse waves, and let me see if I can bring up a picture of that. See, I'm still sharing my browser window, right? And if we go in Wikipedia and we look up electromagnetic wave, we'll see one of these beautiful pictures of the electromagnetic wave.
That's not what I see. I see Vigoro.
Yeah, it's coming up. I think my machine's a little bit slow. Come on. I know you're working on it. Well, okay, there you go. So there's your typical picture of your electromagnetic wave. So in the X direction, they're showing the direction of the electromagnetic wave.
Not seeing it.
No.
Are you seeing the picture now of the electromagnetic wave?
No.
We see
What are you
Vigoro.
seeing?
The Vigoro document.
Okay, then you probably have to wait a second here. The Vigoro is still showing up?
Yes.
Yeah.
Let me try again here. Okay, so did I turn off my sharing? Just see whether I can get a picture to show up here. Okay, now, do you see the picture of the electromagnetic wave?
Blank now.
It's blank? It's just plainly weird. I think I may be having some bandwidth difficulties. Let's try one more time. Okay, how about that?
Go blank.
Is it still blank? But it's not showing the Virgo experiment anymore.
It shows nothing. Your face.
Nothing.
Your face.
Just shows my face. Let's see here. So it's like I'm not sharing at all. So if I click on stop sharing. That's weird that you guys can't see that. How about if I share that? Are you seeing the science chat notes?
No.
Are you guys seeing the science chat notes we were just talking about?
Now we got something now. Yes.
Okay, so you can see that. You can see the science chat notes, right? So why is it you can't see my web browser? Really weird. Do you see the topic electromagnetic radiation?
Blank again.
Unfortunately, yeah. All gone.
Are you guys seeing that? I'm not quite sure what the technical problem here is.
Nope.
No, you still don't see it? Okay, well, you've all seen it anyways, so you know what I'm talking about, which is that they show an alternating electric and magnetic field, right? That goes in a transverse motion. And this is supposedly been derived as part of Maxwell's equations. Is that correct, Harry? Am I describing this at all correctly?
Well, that depends on your viewpoint.
Just trying to explain the mainstream viewpoint here.
What they do is they take the curl equation from Faraday's law and the curl equation from Ampere's law, and they take the curl twice. And what they do is they get a wave equation for the magnetic field vector And then they, from a separate procedure, they get a wave equation for the electric field vector. Okay, and then they marry them together by saying the impedance of space is 377 ohms resistor. And so the magnetic field and the electric field are in phase.
So in physics, what exactly do they mean by a curl equation? I know if I have an electric charge, it puts out a field that decreases by 1 over r squared, and that could be represented by like a vector arrow heading out of the charge. But what exactly do they mean by curl?
Well, that's a complicated vector operation. I suppose Hans might be able to explain that better than I can.
I see now some web page, the Weber bar.
The Weber bar.
The Weber bar.
Boy, that's like way behind. Maybe if I just leave this page up here, eventually it'll catch up. Yeah, that's weird that this would not work. I have never had that happen. But now, but Harry and you and David have been getting into some fairly complicated discussions about whether this is possible or not. So what is your...
That's not really what the discussion is about.
Well, what exactly have you been discussing with David?
The discussion, what I'm saying is that the derivation isn't very convincing because when you take the curl of the curl, okay, in essence, you get a wave equation for the electric field. And then you do the curl of the other curl equation. So in other words, you take, you differentiate first, in effect, basically, you differentiate Faraday's equation twice, or you can differentiate Ampere's equation twice. And when you do that, you get a wave equation. But you only get a wave equation for the electric field, or you get an equation for the magnetic field. You don't get an equation that gives both. You understand that?
So are they cheating? I mean, you're basically like, you know, coming up with two completely unrelated wave equations and then just arbitrarily gluing together. It sounds like what's
well, that's my
and
point.
the arbitrary
My
gluing
point
together
is
is not legitimate.
It's not particularly convincing. And then you get this confusion that what's called the rolling wave confusion, which is that because the textbooks say that an electric field creates a magnetic field and a magnetic field creates an electric field, if you go by that description, then the field should be in quadrature or 90 degrees out of phase, which is incorrect. So apparently, a lot of people get confused by this. That's the point there. In other words, this is it's kind of confusing, and I've had I've discussed this with people, and they'll say, "Oh, you're wrong if you say that they're in phase. They've got to be out of phase." And you can go to various different people. I've had these conversations where people have argued with me about it. So it's the point I'm bringing up there is that that's a point of where people are confused. You can get the wrong impression and get confused. So it's a point of confusion. That's really.
Well, is it a point of confusion, or is electromagnetic theory just wrong?
Well, it depends on your point of view.
Respect. Well, what is your point of view? Is the electromagnetic theory, you know, I think more chance of it being right or more chance of it being just wrong? Do electromagnetic waves actually travel like this?
Well, I think we know that electromagnetic fields are described correctly in that drawing, at least as far as the drawing goes, which is a pretty primitive drawing, in that the electric field and the magnetic field are in phase. They have to be, and I've explained this. I think I've explained it to you. I've explained it to a lot of different people. If they're not in phase, then you would have a power factor involved. So the amount of power transferred is the power in the electric field times the power in the magnetic field. And if they're not in phase, then you've got no power being transmitted.
I think that is so. Basically, you have a pointing vector. I think some of the confusion arises because they look at a differentiation with respect to time of one of the fields causing the other. And they were saying, if one is sinusoidal, well, therefore, if you differentiate, you get a cosine, and that's 90 degrees out of phase. Now, I think you're right. The E and H are in phase. And what causes the difficulty frequently is that if you look at the equations, it's back to the old curl thing, the rotation. It's actually the curl that is out of phase with the curl of one of the fields is out of phase with the other field. But the two fields are actually in phase. It's the curl of one that's differentiated, not the actual field itself. And I think that frequently causes the confusion you've mentioned, Harry.
Well, I actually hadn't thought about it that way. That's an interesting view of it. I have to think about that a bit more.
Yeah, I have to look at that myself.
Okay, now to get to the point here, Franklin, of what the point is about. What David is saying is David's looking at this whole issue from the point of view of he has an ether theory. And he claims that his ether theory does a better job of producing an EM wave that gives the correct phase relations between the E vector and the H vector than the other ether theories do. And that's the point that David is making. My particular position is that I make no assumption about a particular ether. And so since I make no assumptions about what the ether is or what the ether mechanism is, then that's all I'm interested in. I'm not particularly interested in claiming that this particular ether theory works or doesn't work. But an ether theory stands or falls on whether or not it can match the known facts of how a wave is propagated. And the problem is that they don't.
Okay, now David's stick is that he thinks that the ether is in a DNA helix type arrangement, but still a positron electron type ether. So I didn't quite get that though. That was he was using that in particular to justify the EM waveform.
David's theory, you have to understand here, okay, that the problem with ether theories is that you get when you have a solid ether or there's this issue of whether it's like a jelly or a jello or whether it's a fluid like water or whether it's a solid. Okay, and depending upon which one of those structural ideas you employ in constructing your ether, you get different types of wave propagation. Okay, and then you have to make sure that your mechanism of wave propagation through the ether conforms to what we know about EM theory, which is it has to look like that diagram that's shown there. The waves have to be in phase. Well, some types of ether, you get longitudinal waves, and we know EM isn't a longitudinal wave. Some types of ether give transverse wave, and others give combinations of the two. And so you have to make your ether work, to the known facts of electromagnetism. What David is saying is that he's come up with a scheme that he claims satisfies those requirements. He says that the Eupola doesn't, and the other ethers that are being discussed don't. So he's advocating for his particular ether model, and he says that it satisfies the requirements. I'm kind of
Okay.
skeptical. I mean, and
Well,
other people are skeptical too.
Of course, in my part, I'm gonna. What I've been trying to add in this whole discussion is something also entirely, completely radical, which is my point in the emails is that I don't believe that that electromagnetic radiation propagates in this manner at all, and that my claim, which is completely not supported by anything in mainstream or by anybody, just me, is that there is actually no electric component in the electromagnetic wave, and there is no magnetic component in the electromagnetic wave. My point is that all the wave equations that were derived to figure this out are just things on a chalkboard that look like they might work, but in reality, if electromagnetic waves traveled in this fashion, and if magnetic fields could create electric fields, then we should be able to create radio waves with like a transformer loop. And a transformer loop will create a time-varying magnetic field, and therefore, by these equations, should generate the corresponding electric field. And therefore, that should look like a radio transmitter, right?
It was settled by Marconi over 100 years ago.
Yeah, see, Marconi, he tried transmitting waves using magnetic fields, and it does work, but only for very short distances. I mean, this is how they're proposing to, transmit electricity across short distances. This is how your Sonicare works. It's actually like a transformer where the collapsing electric magnetic field induces an electric current in a nearby coil. And we were having discussions about, well, are radio receivers magnetic wave receivers? And the answer is no, not really. I mean, these things, the magnetic wave definitely exists separately from the normal radio waves that we see. But my point is that if electromagnetic waves really were generated by the time-varying magnetic field, because we can definitely create time-varying magnetic fields, that should generate radio waves, but they simply don't. I mean, that would be a prediction of this electromagnetic radiation, is that if I created just a time-varying magnetic field, or if I created just a time-varying electric field, that should, in theory, generate the corresponding magnetic and electric waves. But they don't. So I'm saying that this entire picture, are you guys actually able to see the picture now? It says electromagnetic radiation. But that never show up.
Yeah, we can see it now.
But
you see it. It's small.
Yeah, that entire picture is completely wrong. That's my point. Now that's because, as Harry says, it kind of depends on what your ether says.
Unfortunately for you, Franklin, Marconi pretty much disproved your theory and demonstrated the existence of radio waves, and the way he did that sort of supports the modern interpretation, and that's unfortunate for you.
Well, perhaps it's all a matter of interpretation, but I'm saying that they don't travel as a time-varying electric and magnetic field. That's what I'm saying. Now, I'm not saying that radio waves don't exist. Certainly radio waves exist, but if they are not time-varying electric and magnetic fields, as shown in this picture, then what are they? So I just claim that the radio waves are merely like sound waves. I mean, you wouldn't think that for a sound wave, that a sound wave has an electric and a magnetic component at right angles to each other and they're switching off. You would never think that. a sound wave works that way. And I think that electromagnetic waves work in a very similar manner. Since I'm kind of a materialist, so I like relating things which are similar as having similar causes. So if you were to take that approach, then if you think that electromagnetic waves are waves, then we would relate them to waves that we know about, like sound waves or water waves. And then we would just understand that as being a local compression or rarefication of the medium. And so that is my claim. Is like, so we can argue about that. It's like, is this entire electromagnetic wave thing ironically have actually nothing to do with electric or magnetic fields? Is it just a simple compression wave or not? I mean, but this, as Harry said, this kind of is related to like my own personal theory of what the ether is, which I think that it's filled with neutral dipoles, and once and as such, they act like a gas. That they're very, for the most part, neutrally charged because they consist of a positron and electron very closely bound. Once they do that they just act just like air. So a radio wave is really just the speed of sound through the ether medium. And that's really all that it is. So who wants to challenge me on that? Is the electromagnetic wave really just an ordinary like sound wave? Because that would be a pretty radical departure.
No, I'm not actually challenging you on that because I accept it. I've looked at this myself, but I think that the same equations apply irrespective of whether it is a sort of a longitudinal compression and rarefaction in some manner, or a transverse variation of electric and magnetic fields. The same thing applies. I mean, you know, I'm just wondering if you consider that the longitudinal nature is a variation of electric fields in the longitudinal direction and magnetic fields in the longitudinal direction, or is it not electric and magnetic at all? I mean, because if you say that it is variations in electric and magnetic field strengths, it doesn't really matter whether they're longitudinal or transverse. You still get the analogy with the speed of sound, because the speed of sound is just related to the elasticity and inertia of the gas or air through which sound is moving. And the same with water waves. And here it's the same here, where you have the capacitive effect is basically the elasticity, and the inductive effect is basically the inertia. But I think there are other elements which have shown whether it's transverse or not. And I'd claim that it is transverse. Sorry, somebody else wants to get in.
I mean, I would think, see, this is the problem I have with this whole transverse business. I mean, if you take a look at what an electric field is, the simplest way to see the electric field is you have an electron, and on the outside of that, it has a charge, and typically, there's just like arrows pointing out saying there's a vector saying what the electric field is. So if you were to say what a wave that has a variable electric field, I mean, you're basically, if you took a meter and you measured, in volts, what the electric field is, it would like vary from like 3 to 5 volts or something like that in space. And it wouldn't look anything like this picture we have here, which is a vector pointing like, straight up, right? Well, because in reality,
Franklin,
you'd have to stick a meter in there that measures
this picture way too literally. You just look at this picture and you take it literally. It's a representation. It's a conceptual representation. Okay.
Yeah, that's my point, and that it is a conceptual representation.
The problem is you're completely getting wrapped around the axle over a very simplified I mean, that's a very, very simplified conceptual representation. It's really just that. Okay.
Yeah, but
Now,
that's what that is my point.
Hold on. What we do know is that if I have we know that the polarization effects are real. Okay. I mean, that's just a fact that you have to deal with. Tell me how a longitudinal wave is polarized.
Well, first, you tell me how this electromagnetic radiation fields. You know, this is the problem I have with this picture because, as you point out, this is just a very simplified.
It's a transverse wave is because they can measure the polarization of the wave. The wave.
Yeah, and the way they are justifying the polarization of the wave is by treating this thing like a rope, right? You're saying that this electromagnetic radiation is a simplified and not really how it actually works. But
Franklin, it's not a rope.
When they justify how polarization works, they show this wave going through like a picket fence. Now, a picket fence is not a is not an analogy to them. They're literally taking this wave, putting it through the picket fence, and saying that is filtering out that.
That's a demonstration of the difference between a transverse wave and a longitudinal wave. It's not a literal demonstration of what light or electromagnetic fields look like.
But that is literally how they're justifying polarization of electromagnetic.
That's how they're demonstrating that a longitudinal wave can demonstrate polarization, or a transverse wave can demonstrate polarization, and longitudinal waves cannot, because you can't get that effect with a longitudinal wave. And you could see that when you look at a longitudinal wave and try to run it through a picket fence. It won't show polarization.
And I'm saying that, you know, this diagram here doesn't actually have any real transverse component in it actually either.
It's a diagram
that way.
It's like Harry said,
but there's no actual transverse component that can be filtered out of it.
So the actual transverse difference between a longitudinality of wave and a transverse wave can be seen in seismology quite clearly.
Because yes, we can see that in seismology, where we can see
there certainly is
actually move up and down. But in the electromagnetic radiation wave, there isn't actually anything moving up and down like that.
You can't see it. How can you tell that? Because
are vector quantities.
We justify that
there
is something moving up and down by utilizing the fact that there is polarization characteristics, and that's a transverse wave characteristic.
And as well as linear polarization, Franklin, you would have to explain how circular, elliptical polarization or circular polarization takes place in the longitude.
It doesn't represent motion, it represents amplitude.
Well, I'm just saying that in my argument, that if the only piece of evidence you have for transverse wave is polarization, that number one is a very indirect piece of evidence. And the only thing you would have to do to disprove that is to show some other way to show that you can have a polarized wave without having a transverse component in it.
I mean,
and that's not that hard to do.
Polarization is shown somewhat down the page. If you go down, you see other graphs, and I think the lower graph there is showing you polarization. If I'm right, if you are on the same.
Let's see here. We've got like things like circularly polarized.
The other point is it's not really an electric wave and a magnetic wave traveling together. It's an electromagnetic wave. It's the two components of the same wave. It's like if you look at the stress and strain in a media, you have the stress, which is an amplitude forward and backwards, and you have the strain, which is lateral to that, which is perpendicular to that. So if you tug on a rubber sheet, you'll or even any component where you measure a strain gauge, you pull on something and you stretch it, the tension will be from end to end, but there will also be a strain that narrows that media and so that's the concept of using a stress and strain gauge even. So you can have a wave going forwards when you tug on it, and that wave will radiate forwards in a longitudinal manner, but you also have a corresponding wave that follows that and it will narrow the object as the wave travels forward. The narrowness of that object, getting narrower on both sides, would be the transverse characteristic moving along with that longitudinal. So they are not separate electro and magnetic waves. It is an electromagnetic wave, just as a stress-strain wave would be a stress and a strain wave traveling together.
Well, that's a new view about that. Like I said, I'm trying to argue that there is actually not that there isn't actually anything electric or magnetic about these waves at all.
The other thing that's
that
different
they are completely equivalent to sound waves.
The other thing that's different about a longitudinal wave and a transverse wave is if you look into seismology, you'll see that seismologists use the speed at which a transverse wave travels and compared to the speed at which a longitudinal wave travels. And when their receiver receives each, they can tell you how far away that incident, that earthquake or whatever vibration caused it occurred, because they travel at different speeds. A longitudinal wave will travel through a liquid and a solid, and a transverse wave will only travel through the solid.
Although people have pointed out that even like in seismology, the transverse part of the wave is actually longitudinal compression wave just going up perpendicular to the bulk travel.
That's right. You have it exactly. You understand now what a transverse wave is. It's a longitudinal wave that's going perpendicular to its travel direction. That's a transverse wave.
Yeah. So ultimately, there's nothing unique about transverse. All waves are compression type waves. It doesn't matter what direction they're heading.
The compression is lateral to their direction of route. It depends on which is stronger, the transverse component or the longitudinal component. But all waves are basically a combination of transverse longitudinal characteristics. In a transverse wave, the transverse component takes priority, is the stronger variation.
But now, as far as I'd claim that, so this is my argument against polarization, indicating that there's a transverse component in this wave. Now, I also argue against transverse because there's this argument that, well, the ether must be solid because only solids can transmit transverse waves, and that is only in a sense like in seismology, right? It's just. If you think that the ether has to be like the Earth and an earthquake, and if you think that transverse waves literally have an up and down component as they do in earthquakes, then you come to this conclusion that the ether must be solid. But of course, I wave my hand through the ether here. It's clearly not solid. Clearly some sort of gas.
That's because your hand is a wave pattern traveling through the solid.
Well, that just kind of defies our usual definition of solid.
You have
It certainly does.
Solid is that my finger cannot pass through this solid object. Now, if you're saying that I have a solid which my finger can pass through, well, you're kind of contradicting the whole concept of a solid. I mean, you can do that, but
Franklin, your finger is divisible. It's not permanent. It will come apart. Sorry.
Now, this is the definition of what a solid is. You see, now the reason why solid is important in transverse is because the particles are not allowed to slip by each other. See, that's why they can carry the transverse wave. It's very important that it has this property that things don't slip by each other. So if you have a solid what everything can slip through, then it no longer has the property that you need for it to sustain transverse waves. So once again, that would not be a solid.
But if you say it's a solid and the only thing that can travel through that solid is waves, then you have to define everything as waves. That's as simple as that. Everything is waves through a solid.
Exactly. Agreed.
Everything is waves through some kind of medium. I don't think it's logical to say that it's a solid. And I don't think it's logical to say that the waves that travel through this medium have any transverse component in them. I think it makes even less sense to say that they are traveling as a time-varying electric and magnetic field, ultimately.
There's a difference between logical and intuitive, and I think what you're speaking of is it's not intuitive because you're not thinking, and you're not used to thinking in that format. But there's the distinction. Is it logical, I mean, or is it just not intuitive?
Our intuition goes towards understanding things that we think we understand, which is like sound waves. I think we fully understand how a sound wave works. There's not any big mystery there. And so our intuition says that, well, maybe light waves work exactly the same as sound waves, but we do have this polarization thing, which doesn't happen with sound waves, right? But my argument would be that polarization, I haven't fully worked this out, but the only thing that you need for polarization is to have your waves travel in basically straight lines. I mean, it's often talked that, light travels in a ray. So if I have my laser pointer, that it travels in a very, very tight ray, a very straight line. It doesn't disperse. Now, that's not something that sound waves normally do. Normally, you can't create like a laser beam of sound because due to the interaction of the air molecules and friction, it always disperses out. That would be the difference between, just like an LED light versus laser light. If you get a light beam, it acts like it was like a pencil or a broomstick, right? Which is not something that we would intuitively consider sound waves doing.
You can't act like a pencil or a broomstick.
No, yes, you can have a pencil broomstick wave. It's just a longitudinal wave that has a very, very finite radius, but it's non-dispersive. So in that way, if you can have a wave that doesn't disperse, then you can have what I call light rays. Now, the only thing you need to have in order to do polarization is to have these light rays. They come in and you have like your picket fence kind of arrangement, right?
Well, but waves disperse.
So if you have that picket fence and they are...
Waves disperse. Waves disperse, so you don't say...
Normally disperse, but I don't think that individual photons...
So if you could create a fictitious wave that doesn't disperse, you could have what you want.
Well, this is what I'm saying. You would have to accept that it's possible to generate this wave.
Well, that's not intuitive.
And it doesn't disperse. I mean, this gets to what people think photons are, right? Because in some ways, they have the wave characteristic, and that if you get enough of them together, that you can measure a particular frequency. I mean, this is one of the topics that's been going on in discussion, like Roger Ryden, I think. He thinks that light is nothing but photons, that they're not actually connected together in sinusoidal waves. They're actually just these individual little pulses that travel through space. And that's how I see light traveling, is that it gets generated, especially visible light, which gets generated due to atomic processes, electrons transitioning. So that the transition generates a singular pulse. And that pulse travels through the ether in a straight line forever. I mean, it never actually disperses. A single electron never actually disperses. This is why we can see stars from 8 billion light years away,
Well, this
because the photon doesn't disperse. It comes straight at you.
Years ago. Years ago, this whole thing has been dispensed with years ago. You're just rehashing hundreds of years of physics. What you're saying was disproved years ago. Get up to date. Okay?
Well, the problem is that I believe that this is where the physics wrong term was made.
You have no facts to back up what you believe. You're basically constructing a world of physics out of your fantasy world that you believe ought to be right because you say so. You know?
Well, I'm building this fantasy world out of
no knowledge to back up anything you say. So I would prefer we close the discussion so I can eat lunch.
Well, the experimental facts, I keep on challenging people that if they think that the radio wave has an electric and magnetic component, then you should be able to measure that.
You say there's no polarization.
And I keep on saying polarization.
You deny it.
Polarization does not prove anything about transverse waves.
Well, then you're not doing science. You're just doing fantasy.
I mean, that's the only piece of evidence you have for this is polarization.
It's the crucial piece.
Do you have any other evidence other than polarization?
But you also have interference phenomena, which you haven't discussed and completely ignored. And so waves interfere.
Well, interference phenomenon is
interference effects all the time.
Yeah, interference effects are explained just like sound waves. Sound waves interfere, light waves interfere. They are the same phenomenon.
You're just making up stuff as you go along, Franklin. You just basically pick and choose what experiments you want to believe or not believe, and then you just basically construct your fantasy based on that. Okay? You have to deal with the reality of what is factually demonstrated, and you don't.
No, I'm only going on what is factually demonstrated. I'm looking at the facts, and I can explain the facts in different ways.
I think it's time to eat lunch.
I mean, the problem here is that I'm pointing out that there may be a really, really big problem here in mainstream physics. So that we're all looking at the electromagnetic wave as if they had this kind of, that can be, written, just shown by this diagram, which I think is utterly ridiculous.
You have a factually demonstrated wave that's non-dispersive?
Well, that's what a laser beam would be. We can shine a laser beam over the Earth, the Moon, and back, and it doesn't disperse that much.
It's focused about its transversal center point of travel, but it's not. It's dispersive. It's dispersive.
No, I don't think so.
It's dispersive perpendicular to its direction of travel.
A light ray is completely, like a bullet, non-dispersive.
If it's non-dispersive, then how does it travel through two different slots at the same time? A single ray.
It's non-dispersive because we can see light waves travel for trillions and trillions of miles and still see them. If there was any dispersion, we would see all those stars as fuzzy objects, and we do not.
Its transversivity is focused about a line, which is the ray. It's like I said, when you do the dual slit experiment, a single photon can pass through two slits. How does that happen if it's not dispersive?
You
can get dispersion. Now, this is a completely different thing, which is that the wave gets dispersed by the slot. I mean, you don't even need two slots to get dispersion.
Please.
It's actually it depends on the width of the slot and how deep the slot is, because the photons are interacting with the edges of the experiment. But if you were just to fire straight and it didn't interact with the edges, it would go completely straight.
Please make a difference between probability waves and electromagnetic waves. They are not the same thing. The double slit experiment is about probability waves.
Well, there's not anything probable about those waves. Those waves actually happen in actual experiments, so there's nothing probable about them.
No. these are phenomena both obeying standard field equations. They obey the same mathematics. And you call them, and you mix them all through together. Electromagnetic waves are phenomena caused by the electromagnetic fields. And
I say that's false.
particles can, and photons can, because they are kind of particles, they can obey probability waves in groups, not as single particles, but as groups. A swarm of particles can obey a probability wave. That's why the double slit experiment works.
I'm not quite sure I still follow that. But okay. Well, let's see here. Do we have any edit the comments about whether we think the electromagnetic theory is correct, or could it be that we have it completely wrong, as I'm trying to argue?
I agree with you, Franklin. I've always thought that EM waves are longitudinal, but I've always had a problem with the polarization. And I would like to see you explain polarization maybe with a few diagrams, because I wasn't quite following what you were trying to get at.
If you go down,
this way, okay? Can you let me explain how polarization works? Okay, let me explain, because it's important, because you do have to come up with a legitimate explanation for how polarization works. Okay, now to me, a polarizer is just like the slots between my hands. So if I have a whole bunch of slots, it is like a picket fence, except they're all lined up very closely. So if I take a broomstick, and that's why I'm saying light has to be like a broomstick or like a pencil, and you fire all of these broomsticks in random directions at this set of picket fences. Now, the only thing that's going to be able to make it through that is if it's going straight through the slot in an up or down vector, right? Anything going to the side is going to hit the picket fence, and it's not going to be able to get through, right? So it's going to take all the random directions of all the broomsticks, and it's going to polarize them so that they can only be going in an up and down slot, right? Now, suppose that then you put it in another set of picket fences, which are going the other way. And now that will only let broomsticks, which are heading in either, in a planar, in a plane, only heading to the left or to the right. It will block anything that's actually going up or down. So if you put these two polarizers against each other, that will completely block the passage of any broomsticks through the crossed polarizers, except for maybe if you shot a broomstick straight, absolutely parallel to the surface, it might get through both polarizers in that case.
Perhaps you could look at the
very little. But
Perhaps you could look at the micro wire polarizer.
Looking at how polarization works, and it only requires light travel as a ray.
Perhaps you could look at the micro wire polarizer. You know what the micro wire polarizer shows? It shows that the light passes.
Well, I have been looking at that. Now, the thing about the polarizers is that I've been thinking about polarizers as being like this long set of picket fences. But what a wire polarizer is, and I'm still surprised this actually works, it's just a series of closely spaced electric wires.
That's right.
So there's nothing optical about that.
Right.
All it is, and these wires aren't even
characteristics of the wave.
These wires aren't even connected to each other. They're just spaced wires.
Exactly.
But yeah, this is also able to polarize light, which is what I would admit is contradictory, because then you think if it was only just a single wire, that it would allow you to get in at different angles, that there's nothing really super long, not unless the width of the wire is wide enough to do that.
See, it's because it works on the electromagnetic characteristics of the induced field into the wires. And micro wire polarizer actually polarizes the photons perpendicular to the direction of the wires, unlike a fine slit polarizer, which polarizes it in the same plane as the wires. So you have a polarizer that actually goes perpendicular to your picket fence theory because of the electromagnetic characteristics. One passes the magnetic portion and the other passes the electric portion. Good evidence for electromagnetic characteristics of the light wave.
Well, I would have to agree that that is possibly one of the more actual evidences that there's an actual electric component in the field, which is why I've been looking at it. I mean, I've been playing around with polarizers myself, and so I've got like a piece of circularly polarized material here, and you can see it does weird things. And I have even a piece of quarter wave that I got from my from your 3D goggles, and it does all kinds of really bizarre things depending on how you orient these things. So I am continuing to do it, but the evidence on wire polarizers is very interesting. I haven't been able to, because that I would agree is an actual evidence of there being an electric component involved. So I still can't quite figure out, even if you think that that's true, what part of the electric field is it grabbing hold of, and why does it's basically like a mirror to it's not absorbing the photons. It's actually reflecting them as if they were hitting a mirror. So I think you have to understand how mirrors work, but that these wire polarizers are somehow acting like a mirror. Although we're saying that, just regular, sunglass type polarizers, these plastic polarizers are still somewhat based on that they are essentially creating a wire kind of grid. But I'm not 100% sure about how that works. But I would agree that, but I hadn't heard that these polarizers work at a 90-degree angle compared to the other, like a slot. Is there actually a thing called a slot polarizer?
It's and
why would it pick out
grid array?
The
Fresnel array. Etched lines on a piece of glass. But if you want to look farther into how light works, you can always look into how they manage to manipulate light and project it on the movie screens now, instead of having to use projecting a light through a film. How they can now control it to the point where these little tiny projectors can now project enough energy and control the direction and colors of lights as they pass through the filters to give you the beautiful movie screens you see now at the movies.
Are you talking about 3D movies?
They managed to manipulate the electromagnetic characteristics of the light wave as it goes through their filters. That's much more sophisticated than the technologies we just talked about.
So are you talking about regular movies or 3D movies?
Regular movies.
And I know we use regular movies?
Just regular movies. Just, how do they get those colors? How do they get the light beam to bend from side to side of the screen? How do they get the colors separated from one from the other? Or how do they add the colors to each other?
Well, I didn't think that was any more complicated than
how do you get a light beam to bend? How do you get a light beam to bend if it's not an electromagnetic characteristic, and if you're not manipulating a little mirror that's mechanical to reflect it? Study how those projectors work, and you'll learn a lot.
Well, they work on the principle that the light travels as a ray. Really, I mean, this is how they do. Computer animation.
How do they bend
dat het na 5 minuten... Nee, het is afgelopen. Het praktisch is afgelopen.
Afgelopen? What do you mean, Hans? Your mic's open.
Sorry.
It's all right.
I don't think that, projectors like that rely on the fact that the light doesn't bend, that it reflects exactly where you put it. and usually that's kind of an on-off thing anyways. It's not like we're talking about any great deal of precision here. That that kind of depends. But I would be interested in seeing, like you said, like how polarized, like wire polarizers, or is there any other piece of evidence that there's an electric component in the radio wave or the light wave?
It's out there. Study it. Harry, it's time for your lunch. So I think we're done for the day.
No, I just want to say that Franklin is a master at confusing conceptual models, which is what this diagram is. It's a conceptual model that shows a polarized wave changing in amplitude. Okay? It's a conceptual model. It's a conceptual representation. You confuse conceptual representations with physical reality, and you do that masterfully, but you're confused completely and totally in the way you analyze things because you don't know the difference between a model and a representation of reality. You confuse the model with reality itself, and then you say the model's wrong because I don't think reality is like that. I wish you'd stop doing that. But anyway, lunchtime.
It's lunchtime, and you're exactly right. That's what I try and do because I'm trying to tear down that model. I mean, I'm trying to just completely just trash it and replace it with the same thing as sound waves.
That diagram shows polarization, linear polarization. That's what that diagram represents, and it shows the field oscillating and linearly polarized.
Yep, it sure does, and I would say that's just completely wrong.
You don't understand those concepts, Franklin. You don't understand polarization, and so you say that diagram is wrong because you don't understand how polarization works.
Now I just understand how polarization works in perhaps a different way without using that diagram. But that's what we distance science do. We pick out something that the mainstream says it works this way, and then we say, no, it doesn't work that way at all. And then we debate it. That's what we do. I mean, I think it's a serious topic about how actually electromagnetic wave is propagated. Now, maybe it's propagated like that, but to my mind, I'm still not convinced. But that's what we discuss here. So, but I believe it is lunchtime for you guys. So it's only 9 o'clock for me. But I'm going to let you go. We're going to summarize a little bit about what we talked about. So we talked about Hans. He visited the Virgo experiment. I myself also visited the LIGO experiment. And these are incredible large experiments. And we discussed about, what is the nature of this wave that's coming through? Is it space-time bending, or is it really just being compressed by the gravity wave? And we also discussed, with the help of Harry, about exactly how they're how they extract this kind of signal from their experiments, where they do this signal matching thing, where they know what the shape of the thing they're looking for, and then they look at their noisy data, and then they say, there it is, because we were looking for that, right? Of course, the problem is that we didn't generate the original signal. We just kind of predicted what it would be, so we kind of found what we were looking for. And so that kind of raises all kinds of doubts as to whether that was real signal, whether that was noise. But with the announcement that they had found actually traces of neutron stars where they saw this signal coming from, that does make a pretty strong correlation that they are seeing actual astronomical phenomenon, and that just wasn't just noise that just happened to coincidentally happen at all three detectors at the same time, which is the only other way you could really interpret it. Then we kind of got into electromagnetic waves. So I kind of went on my little rant that I don't think that electromagnetic waves travel the way that they do. And so, because like I said, I'm a materialist. I like to think of things intuitively, and intuitively waves travel like sound, which is not transverse. But you do have to justify the one main thing that they're always saying, which is how polarization works, and but there was good points brought up that the way these polarizers work may in fact depend upon the electromagnetic component if it's sensitive going through these wire grids, which might be true. So another area of investigation to indicate. So it's like, I might be wrong, but I'm here to challenge everybody on anything that mainstream might have to say. And that's why we discuss things. So it's been great having you all here. Thank you for your contributions. And if you have any particular topics that you would like to discuss, please let me know. And we'll keep things going. So I'll see you next week then.
See you next week, and